in this video I'm going to be talking about how a guy named Aristarchus measured the distance to the moon and measured the size of the moon by knowing the distance of the circumference of the earth, which was discovered by a guy named Eratosthenes. And I talked about that in a previous video. We can measure the circumference of the earth by the Eratosthenes method, and you can watch the video. It's on my channel. And from knowing the distance from the Earth, the circumference of the Earth, we can know the distance to the Moon and the size of the Moon as discovered by Aristarchus. Aristarchus was around 200 to 300 BC, and he actually postulated that the Earth orbits the Sun before Copernicus did. So I think he should get a lot more credit for that. Copernicus usually gets all the credit for that. He was around 1580. That was way after Aristarchus. But anyway, let's get started. So here's the Sun, here's the Earth, and here's the Moon. And the sun shines its light, something like this, and it casts a shadow. The earth casts a shadow from the sun's light. In these regions, this is the umbra, and this is the penumbra. Okay, so the earth orbits the sun like this, and the moon orbits the earth like this. Get that understood in the diagram here. Okay. So during a lunar eclipse, the moon in its orbit around the earth enters to the shadow of the earth, to the umbra of the earth. And that's whenever a lunar eclipse happens. So during a lunar eclipse, we can measure the distance to the moon and then the size of the moon as discovered by Aristarchus. So how we do that is, we first assume a few things. We assume this shadow right here, the umbra, it's actually like a cone, but if we assume that these edges of the shadow are parallel to each other, and that we assume the moon orbits the earth with on a constant speed on average. So before the lunar eclipse starts, we can look at the moon right here. The moon right here. And this edge of the moon, we can time how long it takes for this edge of the moon, this edge of the moon to get right here. We can time how long it takes this edge of the moon to get right here, to where the moon is no longer visible totally. Where the lunar eclipse, it's pretty much a full lunar eclipse. So it'll look something like this. We can time how long it takes to do that. And let's say it takes 30 seconds. So we know that in 30 seconds, the moon at its speed in the orbits around the earth covers one moon width. And then we would time how long it takes for this edge right here to get right here. And we could find that it takes about the same amount of time, about 30 seconds. So we know that in those 30 seconds, the moon covers a moon width. So 30 seconds later, it covered another moon width. So we know from that this shadow is about 2 moon widths. And given that it's 2 moon widths, we know that the width of the earth is about 2 moon widths. And actually nowadays, it's not precise, it's a little accurate, but we know nowadays that the moon is actually about 4 times, the width of the moon is about 4 times smaller than the earth. But going off this, we can measure the width of the moon to be about 2 times the width of the earth. And given that we know the moon is 2 times the width of the earth, 2 times smaller than the width of the earth, we can measure the distance to the moon by, let's say, here you're standing on earth during a full moon, and you hold a dime in front of your face during the full moon. And here's the full moon. And let's see, let me draw a triangle right here. If you write a ratio between, let's say, here's the distance between the dime to your eye. Let's say the distance to dime to eye over the distance to your eye to the moon. I'm sorry. The distance, let's see. I'm going to come back to this. Hold on, give me a second. Okay, so what you would want to do is you want to hold the dime out in front of your eye during the full moon to where the dime just covers the moon in front of your eye. In front of your eye, it'll cover your moon just like that. You don't want it too much like this or too close. I mean, too far away. You want it to just cover up the moon. And that's because you want to get, let's say, this cone right here. This cone, you want it to be the same cone as this cone, just smaller, just a scaled down version. And given that this cone is the same cone as this cone, that the ratio between its width right here, this circle's width, and this length right here is going to be the same. So, if you know the distance to your hand, to your eye, to the coin while you hold it up, just covering up the moon, and you write that in a ratio against the width of the moon, so it's the dime. The width of the dime. The ratio between your eye to the dime and the width of the dime, let's say dime width, you know it's going to be the same thing as the ratio of the distance to you to the moon over the width of the moon. And let's say that this ratio right here is like 100. Let's say the distance from you to the dime is 100 times greater than the width of the dime itself. Given that it is, we would know that the distance to the moon would be 100 times greater than the width of the moon. And that's about what it is, according to what Aristarchus figured out. And I think that's what he figured out. And if that's the case, the distance from the width of the moon is 100 times smaller than the distance from you to the moon. Then we figured it out. We figured out, since we know the distance of the width of the moon, we figured out how to measure the distance of the moon. And nowadays, it's actually, that distance is about 238,000 miles, which means it takes light at 300,000 kilometers per second to get there. It would take about a second to get there. And building off of knowing the distance to the moon, we can actually measure the distance to the sun, and then measure the distance to nearby stars and then nearby galaxies and faraway galaxies. This is all what's part of the Cosmic Distance Ladder series that I'm making on YouTube. And if you liked the video, like, share, and subscribe. See you later.